All right, so let's take a look at that FRQ from yesterday and maybe go through a little bit of the grading guidance for it because I thought it was kind of a weird one, and I think that it can trip some students up. Somebody came from tutoring last night, maybe thought maybe I was wrong, maybe it wasn't so terrible, but either way, I'd still like to use it as kind of our introduction to get started today. So let's kind of start at the top. I'm going to talk about the point values and what you had to do to get there, and then you'll be able to kind of grade your response. It says a non-conducting thin spherical shell. So non-conducting thin spherical shell, so has no inside, has a uniform charge density, and some weird symbol. I'm not sure if that weird symbol got translated particularly well on the version I sent to you guys or not. And it's outside. It looks like it's supposed to be the sigma for surface density, but it's hard to know. And has no charge anywhere inside. Use Gauss's law to prove that the electric field inside the shell is zero everywhere, and describe the Gaussian surface that you would use. So part A is worth 3 points. Part B is worth 2 points. Part C is worth 5 points. Let's see, part D, E, and F. D and E are 1 point, and F is 3 points. All right, so let's take a look. So I'm kind of hoping that everybody was able to swing at this one and do okay, because it didn't ask for you to have a whole lot. You needed to indicate that, first you're working from Q enclosed equals epsilon naught times the flux. And, I would use a sphere. So, saying, this is kind of telling your grader that you're using a sphere, but because they asked specifically, describe the Gaussian surface you would use, I would say I'm using a spherical surface. They ask a question, you need to answer it. So if we have some, spherical shell, you're using some spherical surface that is inside the shell. So that's R, that's little r. So, indicating you're inside the shell, I think, is important. And then from there, it's pretty easy because Q enclosed has to be 0. So E has to be 0. Now, when it comes to points, they gave 1 point for a proper application of Gauss's law using spherical symmetry, 1 point for a proper description of the correct Gaussian surface. So you had to indicate that you were using a Gaussian surface that was inside the shell. You could have drawn a picture and that would have worked as well. And for completing the response by indicating that E equals 0 because Q is equal to 0. Now, the amount of math you use versus the amount of description you use, they say describe the type of surface, so that should be in words. Use Gauss's law means you had to have Gauss's law as part of your work here. So if you didn't write out Gauss's law, I don't think you're able to get full credit because that's what they were looking for on the first point, that you were using Gauss's law due to the spherical symmetry. So again, 3 points. Let's go to the next part, part B. It says the charges are now redistributed so that the surface charge density is no longer uniform. Is the electric field still 0 everywhere inside the shell? Now, the answer is no. And here's where I think the problem kind of digresses some. The flux is still 0 because you're enclosing no charge. But that doesn't mean the electric field is 0. And I'm going to go back to this portion right here in our law. We're able to pull the E out of this integral only because we believe the electric field is the same everywhere inside the shell. But I don't think it would be if we redistributed the charges. Let's just consider a simple application, a simple idea of redistributing the charges. So what if, here's our conducting shell, and we distribute the charge so that all the positive charge density is on one side. and none is on the other. So we just move all the charges to there. No matter what, this is going to produce some kind of electric field in this direction. Probably this way too. And although it might be more complicated than that, especially if it's spread over a three-dimensional surface, if we have a Gaussian shell that we put inside here, it is true that we will enclose no charge. But it is not true that the electric field is the same everywhere inside this spherical shell. It's going to be stronger on this side than it is on this side. And moreover, it's going to have an electric field that goes into the surface on one side, it's going into the surface here and out of the surface there. This is why the flux is zero, but I don't think we can say that the electric field is zero. So when they say the charge not redistributed, is the electric field still zero everywhere inside the shell? You'd have to say no and provide some justification. They only gave 2 points, and they said 1 point was for selecting the correct answer of no, 1 point was for a correct justification. Their example is with a non-symmetrical distribution, the fields from the individual charges no longer have the net effect of completely canceling inside the shell. Their response is more a per charge question of how we determine the electric field was uniform inside the shell versus how it is with all the charges distributed on one side. But I think you kind of get the point there. So I'd ask if there are any questions, but that's kind of a useless venture. We're going to go on to part C of this problem. All right, so I've always believed that it is this moment where the problem kind of changes and suddenly becomes a bigger challenge. And so it says, now consider a small conducting sphere with charge positive Q. So our conducting sphere is this thing right there. And it says, this conducting sphere is at the corner of corner A of a cubical surface as shown. So we have a cubical surface. I know that means that it's asymmetric, but they're trying to throw you off your game here. It says, for which faces of the surface, if any, is the electrical flux through the face equal to zero? Now look, folks, some of you probably got this and some of you probably didn't. Or, I don't know, maybe some of you understand what's going on. Or maybe just more of you got this right off than I did when I first saw it. But when I first presented this problem to my students, the very first time I was teaching this class, I realized it's a lot. So we have to look at any place where the electric field would not go through the surface. In this case, we have 3 surfaces where the electric field would travel along the surface. Remember, the square has a corner A that is at the center of a little sphere of charge. And I'm just going to draw it like a top-down look. So let's say this is top-down. That's not top-down, Mr. Shelton. That's a top-down look. And the electric field leaves the charge in a pattern like so in all directions. Does that help you kind of see which surfaces are going to have no flux and which ones aren't? Because I'm thinking this surface has no flux because the electric field passes along it. The direction of the electric field is perpendicular to the direction of the area, right? The electric field would travel this way, and the area is that way. That's dA for that surface. So that's A, B, C, D. And I think we can say the same thing about A, B, G, H. I think we can say the same thing about A, D, E, H. And those are the ones that will have no flux. There's 1 point given for each of those. Now, you'd think if that's all you did, you should get full credit, but it says explain your reasoning. So all you have to indicate is what I just said, that the electric field is radial from point A, and therefore there's no electric field that passes through those surfaces. The way their example is, the electric field from the sphere is radial, so it is parallel to the three corner faces. The electric field vector does not penetrate the area of any of the three correct faces. So it says 1 point, you get 2 points for your justification. And I think your 2 points the 2 points are more or less given for you to indicate why the electric field being produced by the charge doesn't pass through those surfaces, and why that means there's no flux. I think that's what gives you your 2 points. It's a total of 3 points. It said 1 point can be earned for a partial explanation or an explanation with a minor factual error. So that seems like as long as you are, basing on reality and doing a decent job of trying to indicate why the electric field and the area are perpendicular to each other, you'll be fine. I mean, if you say if you try to say that the electric field is parallel to the area, you'll be wrong. You can say it's parallel to the face, but remember, area is measured perpendicular to the face. So 5 points there. 5 points. And if you have questions, come see me tonight. That's the best I can do. Let's go on to part D. It says, at which of the corners of the surface does the electric field have the least magnitude? I really hope you didn't stress too much over this one, because I'm thinking, A, it's the one that's in the middle of the charge, so there'd be no electric field there. Now, I'm afraid some of you probably said F, but A is in the middle of the charge. It's only 1 point. F is farthest away, true, but there's no electric field at the center of this charge. And question E, determine the electric field strength at the positions you have indicated in part D in terms of Q, L, and fundamental constants as appropriate. So 0. The worst part is if you actually thought it was F, boy, that was a lot of work, because you had to come up with the distance from A to F, and that's a lot. It's only 1 point too, so it's right or wrong. So, actually, no, I'm sorry. Let me read this again. It says, as explained above, the electric field at point A is 0, but a correct calculation for whatever point is indicated in part D receives the full credit. So if you picked any of those points and you correctly calculated the size of the electric field there, then you would get the point. So it's going to be QK over R squared, but you have to figure out what R squared is. And so for any of the corners that aren't H or D, because those are based on the side length L, like G, you'd have to use square root of 2 times L. And F, well, you guys get that. That's going to be a couple of Pythagorean theorems to get there. So if that's what you did, and you did it correctly, so you wouldn't get the point for D, but you'd get the point for E. Question F is worth 3 points. And it says, given that 1/8 of the sphere is sphere at point A is inside the surface, calculate the electric flux through face C, D, E, F. Now, there's no way to get this point if you've gotten stuff wrong earlier. You really have to get stuff right all the way through. There are 3 faces that have flux passing through them. And here's where I think some students, don't always remember Gauss's law. It kind of has some tricks in it. Q enclosed equals epsilon naught times the flux. It says that point A has the charge Q, but only 1/8 of the charge is in the box. So Q enclosed inside the box is Q over 8. That equals epsilon naught times the flux, and it's asking how much flux passes through one of the available faces. Well, Flux passes through three faces. And it's the same amount of flux through all three of them. So if we assume that the flux is based on those three sides, all we have to do is find the total flux and divide it by 3. And that should be the flux through one side. One point was used for recognizing that the flux is a constant. So basically just indicating that you made an attempt to use Gauss's law in this situation gave you a point. Another point for recognizing, nope, I'm sorry. One point was given for indicating that the flux is equal to Q over 8. 1 point was given for recognizing that the flux is the same through each of the 3 non-zero flux sides. So basically that there was symmetry here, and that each side has the same amount of flux passing through it. And the last was for proper reasoning those two ideas together to produce an explanation for the amount of flux. 3 points. I would be generous in your application of the credit for the first point, but there it is. So I'd say not terribly weird, but I think it's kind of a weird one. But all right, score yourself. And what I would like you to do is to resubmit this, but Boyd pointed out that I didn't have a second submission window. So I've corrected that and given you a submission window in order to submit it.